Hello, this is Dr. Nair, and we are working on Chapter 4. This is Part 2 of Chapter 4, and we are going to talk about stability of cycloalkanes. It was around 1885 that the scientist Adolf von Baer suggested that small and large rings may be associated with what is called as angle strain. Okay? Angle strain means the strain that is associated with a molecule when it deviates from the normal tetrahedral angle of, so for example, if you look at cycloalkane, cyclopropane, it's a three-membered ring. If it were an open chain like this, then you would have a tetrahedral angle at each of these carbon atoms, correct? Because they have an sp3 hybridized carbon atom. If you look at these carbon atoms in the cyclopropane are also sp3 hybridized. However, they are forced to form a ring structure, and here in this case they have a bond angle of 60 degrees rather than 109. So they show a deviation of almost 49 degrees from the regular tetrahedral structure. And this was because Baer assumed that these rings should be planar in nature. Okay, and so in that same way, if we look at the cyclobutane, you see that it has got a bond angle of 90 degree, which is deviation of about 19 degree from tetrahedral structure. And then we have cyclopentane, which is should be the least strained, having a least angle strain, because it's only 1 degree deviated from the regular tetrahedron. Okay? And then continuing with this argument, the cyclopropane should have a much more angle strain than cyclopentane, because see, now it is 11 degree deviated from the regular tetrahedron structure. However, when the experimental data was obtained regarding the stability of cycloalkanes, generally the way we do the stability of alkanes is by measuring the heat of combustion. And so when the alkanes were combusted with oxygen, producing carbon dioxide and water, and when the heat of combustion was measured, it looks like the molecule which has the least amount of strain, or which is the most stable, is the six-membered carbon atom, the six-membered ring, which is the cycloalkane cyclohexane. Okay? As suggested, cyclopropane indeed has the highest amount of strain, and then comes cyclobutane. But unlike the earlier slide where we talked that the cyclopentane should have the least amount of angle strain, but more stable than the cyclopentane is the cyclohexane. So the reason of why this experimental data was observed, or we can explain the experimental data, is by understanding that Baer's theory was wrong for the simple reason that he assumed that all the cycloalkanes have a planar structure, or he assumed that they were all flat. Okay, actually, these molecules are not flat. Okay, so he assumed that they were all flat. However, rings larger than 3 atoms are not flat, and they assume a non-planar conformation so as to minimize the angle strain. And this phenomena is what is called as ring puckering. Okay? And then as the number of atoms increases, they have more possible conformations where they try to minimize the strain. Okay, so cyclopropane and cyclobutane are strained, which was as predicted, but cyclopentane has a little more strain than cyclohexane, and then to reduce the angle strain, they do this phenomena of what is called as puckering. Okay, so basically there are 3 types of strain that we have to look into regarding the cycloalkanes. One is called as the angle strain, which means expansion or a compression of bond angles away from the most stable structure. And then the torsional strain is eclipsing of bonds on neighboring atoms. Okay, so like in last chapter we studied how atoms can eclipse each other, giving rise to torsional strain. And then finally, steric strain, which is due to the repulsive interactions between two non-bonded atoms in close proximity. Okay, so that means there is steric crowding. There's too much of crowding, and that will cause what is called as the steric strain. So let's look at a few of these cycloalkanes in detail. So as we saw earlier, cyclopropane is the most strained molecule, and that is because it has a bond angle. It has a highly strained bond angle of 60 degrees. So in case of cyclopropane, they have what are called as bent bonds. Okay, so in an unstrained alkane, like just a normal alkane like this, propane, the two atoms overlap maximum by pointing their orbitals towards each other, right? However, in case of cyclopropane, the orbitals cannot point directly towards each other. They are slightly bent and they overlap at a slight angle. So that's why the bonds are a little more weaker in case of cyclopropane, and that results in it being more reactive. Okay, so any chance it gets to open up, it is happy to do that. Okay, and then also see the way it's bonded, the hydrogen atoms are eclipsing. Okay, and there is a high degree of angle strain, which around 60 degrees. You can look at the bent bonds of cyclopropane in this slide here. Now, in case of cyclobutane, it has a little bit less angle strain as compared to cyclopropane. Now, the bond angle is 90 degrees. Okay, so there is still a deviation from the normal tetrahedral structure of about 19 degrees. However, you can see that it is not a flat structure as what was assumed before. It is slightly bent out of plane, and this is what we call as puckering, and this results in the hydrogen atoms not really being eclipsed but slightly staggered, right? So that reduces what the torsional strain, and therefore cyclobutane has a little bit less strain than cyclopropane. Okay, the next cycloalkane that we will look into is cyclopentane. Now, in cyclopentane, it was predicted by Bayer that it is completely strain-free, right? But it actually has a total strain of about 26 kilojoules per mole. So even though cyclopentane has almost no angle strain, it still has torsional strain. Okay, so if you imagine the cyclopentane to be just a planar structure, then the hydrogens on these carbon atoms will eclipse and it will have a large torsional strain. So to reduce those torsional strain, cyclopentane adopts a puckered structure where the four carbon atoms, okay, so these four carbon atoms are in the same plane, but this fifth carbon atom, it goes out of the plane, and that makes the hydrogen atoms not eclipse each other anymore, and that reduces the angle strain. Okay, so four of the carbon atoms are in one plane, but the fifth carbon atom comes out. It's almost like an envelope, and most of the hydrogen atoms are now staggered and not eclipsed, thus resulting in a little more stable structure of cyclopentane. But it still has some torsional strain, and that combined gives you the 26 kilojoules per mole. Now we come to the most stable cycloalkane in that experimental combustion data. It is the slide which we saw earlier, where we saw that cyclohexane was the molecule which had the almost zero amount of strain. Okay, so it looks like it is completely strain-free, and that's because cyclohexane again adopts a conformation or a structure which we call it as the chair structure, chair conformation. Okay, that's because it looks like the way cyclohexane adopts the conformation, like which looks like a chair. Okay, if this is the head of the chair, okay, so this part, and then this is the foot of the chair, okay. And if you see, there are a lot of organic molecules which actually exist in this chair conformation. For example, look at, this is the structure of glucose, okay, which is a common simple carbohydrate, and it adopts a conformation based on the cyclohexane's chair conformation. Okay. Let's see if we can practice drawing the chair conformer. So the way we can draw the cyclohexane, so this is cyclohexane, okay. Now, this is a planar structure, but it doesn't adopt this structure. Instead, what it does is forms what is called as a chair conformer. Okay, so see how the structure is drawn. This is the foot of the chair, and this is the head of the chair. Okay. Try again here. The book actually describes how you can draw this, and this is how you have the carbon atoms arranged in a chair conformer. So in this structure, all the hydrogen atoms that are present in the cyclohexane, they are all completely staggered, and the molecule is strain-free in this conformation. Okay. All right, some additional features when we draw a chair conformer. So now we will focus on this most stable molecule, which is cyclohexane, okay, cyclohexane, and continue our discussion based on this cycloalkane. So when you look at this conformation, there are two positions for the substituents, okay. The one of the positions is called as the axial, and the other is equatorial. So if you redraw this structure, okay, see, I have all the positions which are perpendicular to the plane as axial. There are 6 axial positions, and there are 6 equatorial positions. Okay, so I'll draw it separately. This is equatorial, 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 and equatorial. Okay. So the equatorial positions are around the equator of the ring, and axial are perpendicular to this ring. We can have a better picture here. So you can see that here is where the all the red bonds are showing the axial perpendicular to this plane, this ring here, and then the blue ones are the ones which are showing the equatorial bonds. Okay, all right. So make sure that you are able to practice drawing this cyclohexane structure. Both ways. There is a flipped structure also, where if this is your original structure, cyclohexane can actually flip, okay, flip this way to form another conformer, okay, where this carbon atom is now here, and then this carbon atom, okay, let's put a color here so that we can tag it. Okay, so this is my green, so now my green carbon atom is here. So whenever you do a flip, every equatorial position becomes axial, and every axial position becomes equatorial. So for example, if I had a substituent here, right, and when I flip it, so here it was axial, right, and when I flip it, it becomes equatorial. All right, so these are the features of the different conformers of cyclohexane, and we will talk a little more detail about the conformations of monosubstituted and disubstituted cyclohexane in our next video. So make sure you are practicing drawing the cycloalkane with substituents, and also in the both the one conformer, and then flip it to form the